Hello and welcome to the course Climate Hazards and Disaster Mitigation. Today we are going to present the summary of univariate and bivariate flood frequency analysis. So what have we learned so far? We have derived the flood characteristics and applied univariate flood frequency approaches. We understood the concept of compound and concurrent flooding. We also applied copulas to analyze multiple flood characteristics for informed decision making. So what are objectives for today? We'll provide an overview of the distribution fitting for univariate flood frequency analysis. We'll discuss the compound floods and their detailed classification. We'll explore bivariate flood frequency analysis using copula. So to begin with, we saw that how we can model data. So there are two major ways where you can model the data, that is using the probability density function and the cumulative distribution function. So your probability density function will give you an idea of the total probability. If you sum the area under curve, that will be equal to 1. So at a given instant, what is the probability that you can find it out using a PDF. Well, CDF will give you the cumulative probability across the entire variable range. So whatever your variable range is, and you can just find what is the probability of that. Let us say if you want to find 50th percentile probability, then you can simply get it using the CDF. So all probability distributions are based on this, and this will help us in better choosing the distribution for fitting our data. So coming to the parameters of distribution, so the very basic parameter of the distribution is known as the location parameter, denoted as mu. It will give an idea about the central value of the distribution. So if we consider normal distribution, your location parameter mu will be 0. Sigma is the scale parameter, which is showing the spread of the distribution. If you consider a standard normal distribution, in that case your sigma will be 1. So usually N01 is representing a standard normal distribution. So if the data is spreaded too much, it will give you an idea that how the scale parameter is varying. For example, there can be another data with the same location parameter but a shorter scale parameter also, so that properties will change. The third parameter is a shape parameter. In case your shape parameter is 0 for normal distribution, usually your shape parameter will be 0 because it will be symmetric, but there are some extreme value distributions. So this is extreme value type 1, type 2, type 3. So in that they will have different values of the shape parameter. And then there is another rate parameter, which is usually observed in exponential distribution. It will show the rate of decay. Coming to the families of distribution, so there is a normal family which will have the normal distribution, and if you take logarithm of that, so you can see that the negative space is now gone, so you will have all positive spaces. So there can be a 2 parameter or a 3 parameter log normal distribution. So to all the values, if you take log of x and then you model it, then it becomes a log normal distribution. Next is the GV family. So in GV family, that is called generalized extreme value distribution. We have different variables. If your shape parameter is 0, so GV is usually a 3 parameter distribution, but a special case where your shape parameter is 0, that becomes Gumbel distribution. If your shape parameter is greater than 0, it is a Fréchet distribution, and less than 0, it becomes a Weibull distribution. So each of these distribution is used in different applications. For example, you want to model extremes, or you want to model lower extremes or higher extremes, we can use the GV family more appropriately. Pearson family, in that we have Pearson type 3 and log Pearson type 3. These are again log Pearson type 3 is used for modeling extremes, but more so it is used in the United States, not in India. In India, usually the GV family is more preferred. So in this log Pearson, there is a parameter coefficient of skewness which will determine the behavior of this distribution. How to go about the distribution fitting? So first, whatever data you have, that is a observation sample you have created, you go to select which distribution it is fitting, then you calibrate it, that is estimate the parameters. There are 3 methods to estimate the parameter, that is method of moments, maximum likelihood, and least square methods. And we also saw that how to verify. You can compare with the plotted data. So there are empirical or standard distribution, so you can just compare them to check whether you are getting the same distribution, and then you can use to check what are the quantiles. So here prediction does not mean future prediction, rather it just means to say that what is the likelihood of a value to occur in a certain time span. So here your QP is a discharge quantile of a specified probability, mu is the mean, ZP is the standard normal variate, N01, and sigma is the standard deviation. So if you estimate the parameters, then you are very you can analyze what is the function quantile which are estimated. We saw the Gumbel's method, which is used for univariate distribution. So Gumbel's method, in that we work with the AMS, so that is annual maxima series, which will give you the largest value of 365 daily flows, and then we can calculate return period using the equation xt equal to x bar plus kt into s. Here your kt is a frequency factor, and which can be estimated as minus under root 6 by pi 0.5772 ln into ln t upon t minus 1. There is another way where you can use the distribution not going by frequency factor, you can go by the distribution parameters, and then also you can estimate what is your xt value for a given return period. If you revert this equation, if you are given a particular magnitude, let us say xt is given, and then you have to find t, then you can revert this process and you can get t. So in that case you have to find kt equal to xt minus x bar upon s, and this kt value you can substitute here and you can get the return period. Then we also discuss mean annual flood. So mean annual flood by definition is the 2.33 year return period flood that can be obtained from the graphical frequency analysis. So here on the x axis we have the recurrence interval, y axis you have discharge. If you plot them, whatever value is corresponding to this 2.33 year return period, so that will give you the mean annual flood. So mean annual flood, the physical meaning is, so it's so that is the flood likely to occur annually. So that flood is likely to occur annually, that will give you the mean annual flood. So if you take the mean of AMS series and if you fit a Gumbel distribution to AMS series and you take value for 2.33 year return period, these two values will be same. So that is how it represents the mean annual series. If I just go back in this equation, if you put t equal to 2.33, or if you put let us say xt equal to x bar, then what is your kt value? Your kt value becomes 0. So in that case you put here kt 0 and you find t, your answer will be 2.33 year return period, and that is how we can confirm the same. Then we also discuss compound extremes. So compound extremes are the simultaneous or concurrent or coincident hydrometeorological extreme events which have broader implications on the human, environment and the society than the individual extremes. So the like for example rainfall, there is extreme rainfall and there is storm surge. Both of them can combine to form a compound flood event. So that will be very severe case. If they are considered individually, they may not produce that impact, but when they are considered jointly, they produce a larger impact. Similarly, if there are high temperature and there is precipitation deficit, then the compounding of drought and heat wave extremes. So that is another compounding event. So but compound flooding is one of the major challenges which are facing today. So the compound events are essentially defined as in three different cases. Number one, if two events or more events are occurring simultaneously or successively, that is the first criteria. Second, combination of events with underlying conditions that amplify the impact of events. So if there are some preconditions so that amplify the existing condition, then that can also be a compound event. And third is combination of events which are not themselves extreme, but they lead to an extreme event when they are combined together. So that is how an extreme event can occur. So here we have shown some different examples where heat can be translated into extreme precipitation, and then that is a compounding effect. If there is a cold weather that is added and heavy rainfall is added, then you have a cold front, that is a compounding effect. So like that you can check what are the compounding effects which are there. Let us discuss the detailed classification of that. So the very first classification is the preconditioned event. So what are preconditioned events? So in preconditioned event, there is a driver which interacts with a certain precondition, and there is another driver. Both of them combine to create a hazard, and that has a large impact. For example, let us consider your precondition to be higher soil moisture. So if the soil is fully saturated, there is, let us say, moderate rainfall also, then it will generate higher runoff, and on the other hand there is higher rainfall or there is higher stream flow which is there. Both of them combine to generate flood damages, and that can have flood impacts. Second case, if we consider instead of higher, if there is lower soil moisture, so lower soil moisture, then that becomes a precondition. Then one driver can be deficit precipitation, which and the second driver can be for instance there is extreme heat. So extreme heat and deficit precipitation that accompanied by lower soil moisture can increase the risk of wildfires, and that can impact the forest. So this is how your preconditioned event essentially interacts. Next is a multivariate event, where there is a modulator. It will push the driver, and that can cause multiple hazards. For example, if there is a El Nino as a modulator, then what does El Nino will do? El Nino will result in deficit precipitation or drier conditions, and that can result in heat waves at some location. Then it can result in drought. So there can be simultaneous heat wave and drought, and then they can impact the crop systems globally or regionally depending upon the impact. Next is temporally compounding, where you have a modulator. It enforces a driver and the hazards. Now in a fixed geographical region, they will temporarily compound over a certain period of time. So this time period delta t will be there. That is one coming after the other. So let us say if the modulator is La Nina conditions which are bringing heavy rainfall, so you will have heavy or atmospheric conditions are such that there is heavy rainfall. Then it can result in rainfall in catchment 1, then rainfall in catchment 2, and then they can accumulate at a certain time, and then they can cause floods in these catchments. So these catchments can result in pluvial or fluvial floods, and then they cause widespread flood damage. And last is a spatially compounding event. A spatially compounding event, again the role of modulator. It can create a single or multiple drivers over multiple regions, and it can cause several hazards. For example, again if we have El Nino, so this El Nino can result soil moisture levels, and there can be formulation of other excessive heat conditions, so that heating is there. Then it can cause either drought, or it can cause heat wave, or it can cause wildfire. So there can be a multiple events which are spatially compounding. It can be drought also, it can be heat wave also, but there are multiple events which are concentrated, which has a widespread impact. So spatially compounding events are having a lot of widespread impact. Coming to the conceptual risk framework, so in this framework we have to identify the climatic and non-climatic drivers which are affecting a particular process, and we have already seen this diagram where hazard, vulnerability and exposure will yield the risk. So your multiple drivers will determine the, for example, precipitation and discharge will determine the water level. Then we have the dependent structure between them, and the dependence can be ascertained, and their joint impacts can be analyzed. So the compound floods, when we talk about, so presenting two cases here. One can be compound pluvial and fluvial floods. So in that there is flood in the river that is accompanied by heavy precipitation, and both of them produce a compounding effect. Next is a compound fluvial and coastal flood. In that there is a flood in the river, and on the coastal area there is a storm surge which is ingressing inside the land, and whenever they meet they produce this kind of compound flood. Now coming to the limitations of univariate approach. Univariate approach does not consider dependence between the variables. It assumes stationarity. It does not fully utilize the data, and there is high uncertainty for the rare events, which can lead to risk of misdesign. That is why univariate approaches are not usually preferred. So that is why we'll go with the multivariate flood frequency analysis, because single variable methods are insufficient to capture the entire complexity of floods which are multidimensional in nature, and that is why we require such methods which consider interdependency between these variables. For example, one of the variables can be peak discharge, second can be the flood volume, third can be the duration. So these variables are interdependent, and that is why we require multivariate analysis. So in bivariate analysis, we have two or more design variables which are not independent and are significant in design process. So we consider them and which will lead to more appropriate estimates than the univariate analysis. So you can see that this red one is a probability marginal distribution of your variable y, blue one is a marginal distribution of x, and this black dots, they combine to represent the joint distribution of x and y. So your x variable can be peak, y variable can be volume, and they can be represented as a joint distribution in the bivariate setup. So a copula is a essential statistical technique which is used to work with the bivariate distribution. So the word copula means couples, or it joins two marginal distributions and create a joint distribution. So if the random variables are independent, so this function provides a link between the marginal distribution and the joint distribution is the product copula. So there are two main categories of copula: elliptical copula and Archimedean copula. So elliptical copula involves Gaussian and T copula, while Archimedean copula involves Frank, Clayton and Gumbel copula. So in hydroclimatological studies, so this Archimedean copula are widely used because they can easily model the tail dependence between the extremes. So when we want to model the dependence, we want to quantify the strength of dependence between the variables. So we can do either by using a parametric t-test, or we can go for the non-parametric test as well. So non-parametric test would involve your correlation measures, which will give you non-parametric like Spearman Rho or Candles-Tau. Then you will fit the marginal univariate distribution to each variable to find the suitable PDF. What is the PDF that you will find it out? Then you will select copula families depending upon the strength of dependence. So we have already discussed if there is positive dependence or negative dependence, which copula is best suited. Then you fit the copula, and then you estimate the parameters of copula. Then once you identify the parameters, you find the best fit copula based on the goodness of fit and other performance measures, and after that, selecting the best copula, you can find the joint and conditional return period of the flood events. So what are the highlights of this week learning? So flood frequency analysis provides a probabilistic framework to quantify the flood magnitude and the recurrence of extreme floods. The univariate flood frequency analysis relies on the probability distributions and parameters, and helps us in the quantile estimation. However, they are having certain drawback because they do not consider other characteristics. They are data is underutilized, and which can give unrealistic results in rare events, and can have a risk of misdesign. Compound extremes arise from interaction of multiple hydrometeorological extremes. which have greater impacts as compared to the individual extremes. So we use bivariate flood frequency analysis to model this compounding effect. So copula is one such method which will help in effectively characterizing by utilizing marginals of two variables and creating a joint distribution between them to support informed decision making for flood management. Glimpse for the next hands-on session, will be performing a distribution fitting exercise. We'll use the AMS series for flood frequency analysis using Gumbel's method. We'll compute the correlation measures using Pearson, Spearman and Candle. Then we'll see the copula fitting and how we can calculate the return levels using the copula. So thank you for your attention. In the next lecture we'll meet for the hands-on session on univariate and bivariate flood frequency analysis.